everyone, welcome to Science Friday.
Here's some for E as well. The one on the top here is one of the ways that you can define E.
What makes a field more likely to have an unbalanced gender distribution?
So this can be, like in the case of this paper, gyrification or brain folds.
A neuroscientist started to look at the brain
as like the
more as an
interconnected.
I'm asking incredibly negative consequences.
Hi everyone, so a quick note before we begin. You might have seen some flyers outside in the hallways or the blackboard saying that I will be talking about string theory. For some reason, I think the title information in the database did not update, so I am going to talk about string theory, but that's not what my presentation is centered about, so just letting you know. And so my presentation is called How a Single Particle May Explain the Universe, Detecting for Alps in Galaxy Clusters. And for those of you who don't know me, my name is Vinca. I'm in 9th grade. So ever since the start of middle school, I've begun having existential crises and became increasingly interested in the mysteries of the universe and the meaning of life. You know, why do we exist? Why is the universe as it is? What are the fundamental reasons behind the laws that we observe? And this led me to find the subject of closest approximation to being able to explain the universe. In my opinion, theoretical physics. Sorry to the bio fans here, who I believe to be probably most of you. So this is because I think theoretical physics takes everything we know about the universe and tries to put them in models and explain the reasoning behind them. So obviously I have not taken a theoretical physics course yet, so my knowledge is hand-wavy, but nonetheless, the more I learned about the concepts, the more interested I became. So this is what led me to choose the topic that I will explain today. So first of all, let's look at a map of all of physics. So on the left here is classical physics. This is the everyday intuitive Newtonian physics, like dynamics and projectile motion. On the top here, we have relativity formulated by Einstein. One branch of relativity is special relativity, which deals with concepts like time dilation and E equals mc squared. And the other branch of relativity is general relativity, which redefines our notion of gravity as warps in space-time. And so relativity operates on large scales. And quantum physics down here is the opposite. It operates on the micro scale. Quantum physics describes things like atomic theory and the standard model of particle physics, which basically has several fundamental particles representing everything in the universe. So on the right here is just things that we might delve into in the future, like dark energy and dark matter. So one might expect the standard model of particle physics to be able to explain everything in the universe, right? It has fermions to represent matter, and it has bosons to represent interactions between matter. However, there is one exception, and that is gravity. So physicists have tried to represent gravity at the quantum scale by coming up with the graviton, a potential fundamental particle. But when they tried to incorporate the graviton into the standard model, their calculations resulted in absurd values like infinity. This basically means that however hard we try, we cannot, at this moment, represent gravity at the quantum scale, meaning the two biggest fundamental branches of physics clash. They do not work together. And so this is a fundamental problem, and one of the loftiest goals in physics today, to come up with a theory of everything, to describe the universe, and to make general relativity and quantum mechanics actually work together. So a theory of everything has not been found yet. However, one of the arguably most popular ones is called string theory. So string theory is formulated in 1968, and usually we'd expect particles to just be points in space, but string theory represents fundamental particles as a certain vibration of a microscopic string. So the different properties of the string, like the frequency of vibration and the tension, would result in different values of properties like mass and charge for fundamental particles. And so the scientists actually were able to find a type of vibration of a string that would represent the graviton, thus representing gravity at the quantum scale. And this means that string theory, basically, if it were true, it would be able to completely resolve the clash between relativity and quantum mechanics. And string theory is a very elegant theory, and a lot of physicists wish it were true, and some think it's too good to be true. But one of the caveats is there's no experimental evidence of string theory yet. So I've just repositioned the map we saw earlier to relativity over here, quantum mechanics, and as I've said, string theory is a potential solution to unite the two. And let's put that thought to the side for a moment. And there has been another very fundamental problem in physics called the CP symmetry problem. It's a very complex problem and deserves a whole other presentation of its own. But basically, it results from the standard model in special relativity. And if this problem were proven to be unresolved, then that means we'd have to rewrite special relativity and the standard model. Solving this problem would basically preserve the integrity. So this is a very important problem to solve. And two people called Pei and Quinn did come up with a solution for it. It's a hypothetical solution, and it predicts and uses a particle called axion-like particles. And this is also a theoretical particle that they predicted. So the interesting thing is that string theory also happens to predict this particle, axion-like particles. And on top of that, the issue of dark matter, what represents 80% of our universe that is undetected, also happens to hypothetically use axion-like particles. And on top of all of that, additionally, there's the issue of the antimatter-matter imbalance at the beginning of the universe that also uses axion-like particles. So this is all to say that this one particle, hypothetical particle called axion-like particles, single-handedly results from and deals with several fundamental theories of physics. So if, let's say, the axion-like particles were proven to be non-existent, if they were disproven, then that means all of these theories would collapse. So, oh, and also, fun fact, axion-like particles were named after the laundry detergent brand called Axiom because they supposedly cleaned up the problem. So you can probably see why physicists would be very eager to conduct experiments to detect for these axion-like particles, right? They're completely theoretical. And so axion-like particles, we don't know a lot about them, but we know that they have an interesting property. So when they're traveling in the presence of a magnetic field, and if they're traveling near photons, then they would interact with the photons, and this is called coupling. They'd basically convert into photons. And so can anyone venture a guess as to why this is an important property? I'll give you a hint. So on one hand, we have axion-like particles. I'll just call them ALPS as an abbreviation. On one hand, we have ALPS, right? A completely theoretical particle that we wish to detect. And on the other hand, we know that ALPS interact with photons. Photons, doesn't that sound a bit familiar? It's light, something that we can observe, something that we have devices like spectrometers to detect. So does anyone want to guess now why you think this property is very important? No takers? Michael?
If you were to hypothetically take a body you think could be an axion-like particle and have it interact with a magnetic field and a photon and then measure the light coming out, you get a compelling evidence that some kind of reaction took place which could potentially be.
Yeah, so exactly. So what Michael said is that basically by observing the photons and having potentially ALPS interacting with the photons, we can detect that interaction from our devices. So this, I will be talking about an experiment called the Chandra X-ray experiment ran by NASA, and this experiment is one of those that tries to detect for the presence of ALPS. So this experiment was published in early 2020, and it lasted over 5 days. And it was basically observing a galaxy far, far away, aka the Perseus galaxy cluster. It's 240 million light years away. And it was basically observing the X-ray photons that came from the active galactic nuclei in the middle. So they used the basic setup of a spectrometer where it took in the X-rays, bounced it off a diffraction grating, and so that split it into its multiple wavelengths, and then analyzed the data from there. And so, as Michael said, we basically, to see if ALPS are really hanging around in this galaxy cluster, we take the light that we get and we compare it to the light that would have been there without the interference of ALPS. Because ALPS, remember, they couple with photons, so they convert to photons, right? So if ALPS do exist, then we know that there will be a surplus of photons in our data that wouldn't be there originally. So here are the results. So let's look at the top panel first. On the x-axis, we have the energy of the corresponding wavelengths of the X-rays that NASA detected. And then on the y-axis, we have the flux, basically the flow rate of the energy. And so if you can see this pink line underneath the data points, this is the theoretical model if ALPS did not exist. So scientists basically understand how the flux would correspond to the energy of the X-rays without any distortion from the ALPS. And so these data points on top are basically the experimental evidence with potentially the distortion of ALPS. So if these data points were like way up here, then we know that, that ALPS do indeed cause something to happen because the data would be different from the data without the interference of the ALPS. So over here on the second panel, we basically divide the experimental data by the model. This basically says if they're the same, if let's say ALPS did not exist, so they provided no distortion to the data, then it would be the same as the theoretical model underneath. So dividing them would get values close to 1. And this is actually what happened in the Chandra X-ray experiment. If you can see, all of these values are within the margin of error of 1. So this basically means that within the margin of error, Chandra X-ray did not detect any ALPS. So another point of this experiment was to lower the range of the coupling constant. So if you guys remember, the coupling constant basically means how strongly the ALPS interact with the photons. So the higher the coupling constant, the more likely it is for ALPS to convert into photons. So and also the coupling constant is a value that is inherent to ALPS, but physicists don't know that actual value, and they're trying to find it with this experiment also. So before the Chandra X-ray experiment, there have been previous experiments done of the same type to try to detect for ALPS, but those experiments had more rudimentary devices, like a lower sensitivity. So they would only be, for example, able to detect the ALPS if they had a coupling constant of higher than this value. So if it were higher than this value, they'd be able to detect the distortions, but if it were lower, then they wouldn't be able to detect it. So after the first experiment of this type was run, they could rule out, since it didn't detect any ALPS, they could rule out the possibility of the coupling constant being above this value, and knowing that if ALPS do exist, then the coupling constant must be lower than this value. So then preceding experiments were done that improved their sensitivity bit by bit and still did not detect any ALPS. And so we got to Chandra now, which is the pale yellow region. And since Chandra did not detect any ALPS either, they could rule out the possibility of the coupling constant being higher than 7 times 10 to the negative 13, because if it were higher, then they would have been able to detect it. So from this, we know that if ALPS do indeed exist, then the coupling constant would be lower than this value. So what are the implications of this? Well, first of all, we do have tighter bounds of the coupling constant. And next, I think the main takeaway I got from this paper was actually the possibility of non-existence. So as a Science News article said about this experiment, if physicists are panning the universe for gold in the form of axion-like particles, they've gotten down to a strainer small enough to snag a billionth of an electron and still not found the gold. So this has implications for all the different problems that involve ALPS. This might be scary for some physicists because all of these beautiful, potentially beautiful solutions to big problems in physics are all hanging by a thread. And though, of course, this does not rule out the existence of ALPS because, again, it could just have a lower coupling constant that we couldn't detect, but this does experimentally weaken these theories, like string theory, the potential beautiful theory of everything, uniting quantum mechanics and relativity. So, but ultimately, we don't know. Maybe the theory of everything is just right in front of us, and we just need to look from a different perspective. Thank you for listening.